Okay, hello everyone. We are very sorry for the delay, and I'm Kai Gu from Nanjing University, and I'm very honored to host this session. And this afternoon we have 6 speakers, and the first speaker is Professor Xuanmei Fan. Professor Fan is a professor in the College of Environment and Civil Engineering at the Chengdu University of Technology. She is a recipient of Richard Ward's Award of IAEG in 2016. Her research interests cover earthquake-induced geological hazards, application of remote sensing and geographic information systems in geological engineering, risk assessment and prevention research of geological hazards, etc. Today, her topic is what have we learned from earthquake-induced chains of geological hazards? Let's welcome Professor Fan.
Thank you very much, Professor Gu, for your introduction. So let me share my screen. Can you see my presentation?
Yes, we can.
Okay, is it on the full screen or on the?
Yes, it's full screen.
Okay. So first, I would like to thank Professor Shibing and Professor Chaoshen Tang for inviting me to give this presentation on the ISEG. So I'm quite new to your committee. I'm working probably also on something a bit different from the presentations from yesterday and today. So as Professor Gu already introduced, so I will skip the self-introduction part. I'm going to talk about the earthquake-induced chains of geological hazards today. So just to give you a kind of a short introduction of what I'm talking about, because I think some of you may not really know when earthquake happen, why it will trigger so many landslides. So I'll first show you a piece of animation. So as you can see, this earthquake due to the strong bounce and a lot of landslides. And this, is it okay? It's stopped, sorry. Just a moment. Yeah, so some of the landslides in the vicinity of river landslide dams. And these dams, they are quite big. So especially the was dam breaking and dam causing. So this is just a piece of animation to give you a direct feeling of it's a type of earthquake-induced chains of geological hazards. So some landslides in the vicinity of rivers can block river and forming landslide dams, and the dams can fill during the, especially when you have heavy rain, and then causing further flooding. And this is this slide shows you the situation of the 2008 Wenchuan earthquake. So this earthquake, you know, occurred in 2008 in the southwest part of China, and with magnitude 7.9. It killed about 87,000 people, and 1/3 of the total death toll was actually caused by landslides and secondary geological hazards. So, and this earthquake triggered more than 60,000 landslides and also induced numerous post-seismic landslides and debris flows. So that's why it has attracted attention from all over the world. This is some literature statistics we did in 2018 at the 10th year's anniversary of the Wenchuan earthquake. So as you can see, there were about more than 6,000 papers published on the Wenchuan earthquake, and about 1,000 papers are directly on the geological hazards induced by the earthquake. So this slide gives you a summarization of the chains of geological hazards in the mountainous regions. So as you can see from here, in the right circle represents for the co-seismic stage is actually what I have already showed you during the animation. So during the earthquake, it can trigger kind of different types of landslides, and these landslides, some of them can causing further like dam breaking, flooding problem. Sorry, I don't know why, but the slide is jumping itself. And some of these landslides after the earthquake can be remobilized or reactivated, and some can even convert it into debris flow and further transport sediments into river. As you can see from here, the riverbed can be rising during the large amount of loose sediments transport from hill slope to the river. And as you can imagine, after riverbed rising, it will also causing the increase of flooding for the future. So since 2008, I have been working on the chains of geological hazards, and I summarized it here. So first, we were working on co-seismic landslides. What I'm saying co-seismic, it means when the earthquake happened, it simultaneously triggers some geological hazards. So we did inventory and analyzed the spatial distribution pattern and their controls. And after that, we were moving like with a timeline to the post-seismic landslides and post-seismic debris flows. So I will give you a kind of short overview of all these stages in the coming slides. So first of all, we are trying to understand, like during the earthquake, why it can cause so many landslides and what is the spatial distribution pattern of these landslides. So we found there are 3 types of controlling factors. The first one is seismic factor. It means distance to fault, fault type, and hanging wall effect, footwall effect. These factors are important, and also like terrain factors, slope, internal relief, etc. And geological factors we all know are lithology, soil type, and geological structure. And the hydrological factors are extremely important for landslide dams, actually. And we also further created an inventory for global earthquake-induced landslides. So this inventory includes 49 earthquake-induced like landslides events. And this is publicly shared with the USGS data repository. And based on this global earthquake inventory, we further analyzed and we found some like kind of general rules for earthquake-induced landslides spatial distribution. As you can see from here, most of landslides actually are concentrated on the hanging wall of the thrusting fault. And it also has very strong distance effect. So within the 5 kilometers close to the fault, the landslide density is the highest. And with the increasing of the distance to fault, the landslide density becoming decreasing. And we further developed a model to predict when an earthquake happens, where most probably the landslides will be. So this model actually used artificial intelligence methods based on this global earthquake-induced landslide inventory. So to give you a quick summary of this model is, for example, everywhere when an earthquake happens, we can quickly predict where most probably the landslide gonna happen. So this figure actually shows after the Geological earthquake, we did a quick prediction of co-seismic landslides, and the model did a quite good job for prediction the location of co-seismic landslides. And moving from the co-seismic stage to the post-seismic stage, So after the earthquake, our government is facing serious problem with post-seismic landslides and also debris flows. So the key research questions we are trying to address here is how to quantify the evolution of post-seismic geological hazards and trying to understand what is the pattern and trend of the evolution of post-seismic geological hazards, and trying to find the possible controlling factors and also create prediction models for future landslide hazards in the region. So first, to understand, trying to understand how landslide activity changed after since after 2008 till now. So we created a multi-temporal inventory for co-seismic, post-seismic landslides. Tracking is an inventory covers the time period for about 12 years after the earthquake. So you can see from here, this figure shows the co-seismic landslides. So all the yellow polygons represents for the co-seismic landslides. And this is the inventory mapped after the first strong rainfall after the earthquake. Different colors, different reddish colors represents for the reactivation of co-seismic landslide deposits, and the red color means the dormant landslides. So as you can see here, in 2011, after a big rainfall event in 2010, most of co-seismic landslide deposits become reactivated or remobilized. And this is the inventory after 2013. You can see the reddish regions are becoming less compared to the 2011. That means we have less reactivated landslides and more regions become white color. That means more regions become stable. And now we did this again for 2017, 2015, 17, and 20. I did not show other inventories. And we also mapped the pre-earthquake landslides. These are 2005 and 2007 for comparison reason. So if I plot all this inventory as a point density, volume density, you can see before the earthquake, this region has quite low landslide density, and this is a co-seismic, means earthquake-induced landslide density. And after that, the density become decreasing. And until 2020, this landslide density, the values seems already returned to the pre-earthquake level. And if we further plot this in this graph, you can even see it more clearly. So we can see that after the earthquake, we have the landslide volume become suddenly increased, and then with time it's decreasing. And so far it has been already returned to the pre-earthquake level. And even considering the variation of rainfall, if we do a normalization with rainfall, you can still see the clearly decreasing trend. And now we also checked the evolution of post-seismic landslides in size. So how the magnitude changed over time. As you can see from here, most of the reactivated landslides are actually represents in this yellow color. So these are the remobilization of co-seismic landslides. And the new post-seismic landslides are the green ones. They are rather small. So the major type of post-seismic landslides are actually reactivation from the co-seismic landslide deposits. And from this graph, you can also see the decreasing trend for the size frequency curve from 2008 to 2020. And 2020 is the green points. They are already very close mixed with the pre-earthquake points, 2005 and 2007. And we are also trying to track how they change on the slope That means how the material are moving gradually from the slope to the channel. So we found this, sorry, let's jump again. So we found these are the co-seismic landslides, and they are mostly concentrated at the upper part of the slope due to seismic amplification effect, all to the channel. And 2011 and 2013, they are pretty followed the co-seismic stage distribution pattern. But afterwards, in 2015, 17, and 18, they again becoming more or less similar to the pre-earthquake situation. So we are trying to understand why the landslide activity decade very quickly after the earthquake, let's say within 10 years, is already returned to the pre-earthquake level. And we found one of the controlling factor is what we call it grain size causing. So we found some field evidence. As you can see from here, this is a cross section we found in the field, reviewed the different debris flow deposits from different years. So the bottom one is the oldest debris flow event, and covered on the top is the next event, and on the top is the newest event. You can obviously see that the grain size become causing for the debris flow events. And from the field photo at the same location, you can also see the fine grains. They are easy to be washed away during the first few rainfall events, and then left the coarse grains. And the grain causing can causing permeability changing of the slope, and also the friction cohesion also changing with time. And we also took samples to do grain size distribution analysis from the field. You can also see with time the grain size becoming causing. It means the deposits has much less fine grains compared to 2008. If you compare the 2019 with the 2008 grain size distribution curve. And then the other important factor is revegetation. It can contribute a lot to stabilize the shallow slope failures. Sorry. And this is maybe we first look at the photo. This is a photo I took in the field shortly after the earthquake for one of the big landslide called the Donkey Ko Landslide. And this is a photo again in the more or less from the same angle. And you can see it was taken in 2020, and the landslide is fully covered by vegetation, and it's hardly to be noticed that there was a landslide about 12 years ago. And then we did a Landsat imagery analysis. You can also see this region become revegetated over time. And if we did NDVI analysis with time for pre-earthquake data and post-earthquake data, you can also see the earthquake-induced landslides destroyed a lot of vegetation, causing the NDVI sharply decreased during 2008. But after the earthquake, NDVI values increasing gradually, and now about 85% of the region has been recovered by vegetation after the earthquake. And then we also did a dynamic analysis for the controlling factors. So as you can see from this dynamic factor importance changing over time, and based on this dynamic changing controlling factors, we created a model to predict the post-seismic landslides. And this paper is published on Geophysics Research Letter this year. So if you are interested, you can check the details in this paper. And now let me move to the post-seismic debris flows. So this gives you an idea of post-seismic debris flows. These two images were taken in 2010 and 2011. You can see during the first few rainfall events after the earthquake, almost all catchments has debris flows, and this is the Minjiang River. Almost all catchments has debris flow deposits in the Minjiang River. So in the first few years, the debris flow activity was quite high. And some of this debris flows also causing a big problem to the reconstruction site, like this debris flow running to the river, partially blocks the river and causing flooding of the upstream reconstructed inshore site. And this is another catchment. After the earthquake, our government constructed like check dams trying to stop this kind of debris flows, but some of this mitigation works was destroyed because of the activity was so strong, and some check dams was filled up by debris. So from this, you may have a feeling that we probably have underestimated the activity and the magnitude of these debris flows in the first few years after the earthquake, when we started designing this mitigation works. And try to understand what is really control the post-seismic debris flows. We created a database for the post-seismic debris flow, including about 500 debris flow events after the earthquake, and also the rainfall data. We have a widely distributed rain gauge network, as you can see the blue dots here. So that helps us to understand the triggering rainfall threshold for this debris flow events. So the debris flow activity actually shows different trend from the post-seismic landslides. As I just mentioned, for post-seismic landslides, we have this clearly decade after the earthquake, but for debris flow events, we see they have these fluctuations with the changing intensity of rainfall after the earthquake. And one of the reasons is if we do a sediment budget analysis, we found that actually more than 80%, 85% of the co-seismic landslide deposits are still in the mountain regions. So that means in the past 12 years, by the already occurred debris flow sediment transport, it only transported about 10% of the deposits outside of the catchment into the Minjiang River, and 5% are actually stored in the channel, and about 80% are on the hill slope. So that's why we still have kind of debris flow activities continue longer than post-seismic landslides. And in order to better predict post-seismic debris flow activities, we created a numerical simulation model, as you can see from here. It can simulate like which part of the co-seismic landslide deposits can become unstable during the heavy rainfall and how they converted into debris flows. So we did this simulation and compared with real scenarios and found this model actually have quite good prediction power. And this paper has also been published in 2019. And for this model, we also shared our codes. It was developed based on the PC Raster open access platform. So if you are interested in the debris flow simulation, especially after the earthquake situation, you are welcome to also to check the paper and download the codes to run it in your own area. And then we further tested our hypothesis before, because I mentioned the grain size causing and revegetation are the two most important factors we think can control the post-seismic landslide activity and debris flow activity. So we tested it with our model, and it shows also the same results. As you can see here, with green size causing the rainfall threshold increasing over time, and also revegetation also placing a somehow relatively important role for the debris flow activity. But for the early warning of debris flow, we need to understand better, like how their occurrence can be linked with the triggering rainfall intensity and duration. So after the earthquake, we had this schematic graph to put our Wenchuan earthquake data with the 1999 Qiqi earthquake data. So as you can see here, this is the rainfall, average rainfall threshold before the earthquake, and after the earthquake, it sharply decreased to only 1/3 of the pre-earthquake level. But with time, it also increasing. And the reason for increasing, I already explained, is because of the changing property of this co-seismic landslide deposits, like green size causing and revegetation, etc. But no one has been quantified the how the rainfall threshold changing. So what we did is we put all these debris flow events, about more than 1,000 events in more than 200 catchments after the earthquake, and trying to see whether the rainfall threshold has a pattern of changing. So this is the pre-earthquake rainfall threshold is quite high. And if we use this threshold to predict post-earthquake debris flow events, you can see only one event can be predicted. The reason is after the earthquake in 2008, the debris flow rainfall threshold reduced to here, and then with time is increasing. So, but so far it has not yet been returning to the completely to the pre-earthquake level. So that's why on one side we still have quite a lot of deposits in the mountain regions, and then on the other side we have the rainfall threshold still not yet returned to the pre-earthquake level. So that's why we will continue have debris flows in the earthquake region probably for another 10 years or even longer. So that's all I want to present today, and just to give you a quick summary for the recommendations for future directions. I also summarized all this study on the paper we published on Reviews of Geophysics in 2019. If you are interested in this part, you can also check that paper. So we think the challenge for the future is to understand like the interaction between different types of hazards. Like the chain of geological hazards, it always involves different types of hazards. So the interaction, trying to understand their interaction and quantify the interaction is very important. And the quantification of post-seismic landslide inventory in time, space, and in magnitude, we already did a field work on this. But the future challenging is to better analyze the controlling factors, and then to also to do it for more earthquakes, because we built our model now mainly based on the Wenchuan earthquake, and then we hope in the future can look into more earthquakes globally. And then for the prediction of post-seismic debris flows, we created a numerical simulation model, but again, it needs to be tested in more regions. Fortunately, we already tested it, for example, in the Geological earthquake and in the Kaikoura earthquake after New Zealand Kaikoura earthquake, sorry. And then the other thing is about trying to create a better model to understand hazard and risk evolving after the earthquake, and trying to apply it in different regions. And then for the long-term impact, we need to create a model together with the geomorphic evolution, trying to understand how the sediment transport and how it affects the long-term landscape evolution. So lastly, I'd like to welcome you to our institute called State K Laboratory of Geohazard Prevention and Geoenvironment Protection. It's China's only national level laboratory in the field of geohazard and engineering geology. And we are currently recruit new staff members. So if you are interested, you can directly contact me. And we also have a team focusing on the chains of geological hazards in the Tibetan Plateau regions, leading by myself. And then another small advertisement is about our annual course. We have an international research association for large-scale landslides, and this research association offers free course for PhD students and young postdocs for the large-scale landslides, field data collection, monitoring, modeling. So we already organized this course since 2016, and last year we organized the online course. And this year, we already opened the call. It will be online course again, but we will have some lectures and the training session for modeling software. And we also have a virtual field trip to lead you to some of the sites which I also presented in today's presentation. So if you check our website, you will find this information. And thank you very much for your attention.
Okay, thank you very much, Professor Fan. Well, the time is perfect, and we all know that earthquake is not a single geohazard, but it can change a lot of, it can induce a lot of other geohazards. So Professor Fan provided us a very comprehensive understanding of the earthquake-induced chains of geological hazards. So we have time for one question. Do we have any questions for Professor Fan? So you can raise your hands and so do we have any questions? Okay, no. So thanks again, Professor Fan. And if you have any questions, you can email to Professor Fan and have conversation privately.
Okay, thank you.
Okay, thank you.